introducing me so wonderfully to our audience. And thank you, Petroleum Engineers Association, for inviting and giving me this opportunity today. Dear students and fellow professionals, thank you very much for joining us today for this webinar. I hope it will be useful for all of you. Knowing that the audience comprises of people not belonging to the geosciences background as well, I have tried to simplify things as much as possible. Please feel free, like Chata mentioned, to type your queries in the chat box. They will be answered at the end of the webinar. The topic of my presentation for today is Interpretation of Basic LWD and Wireline Logs. As the title suggests, I will be covering only the basic logs today. The advanced logs such as FMI and NMR are currently out of scope of this presentation. Moving on to the agenda of the webinar, I will begin by giving you a brief idea of the LWD and wireline logging, the concepts, differences, and their objectives. This will be followed by a section on interpretation of the basic logs such as caliper, SP, gamma ray, resistivity, density, and neutron. The final sections will cover qualitative and quantitative interpretation of the logs. LWD and wireline logging concepts. Coming to the concepts of LWD and wireline logging. LWD is short for logging while drilling. It is the measurement of formation properties during drilling. It is a technique of conveying well logging tools or sensors into the wellbore as part of the bottom hole assembly. The figure is an example of an LWD tool provided by Halliburton. It conducts the directional survey as well as measures total gamma ray of the formation being drilled and simultaneously displays data to monitors at the surface. The next is wireline logging. Wireline logging is the measurement of formation properties after drilling of a section is concluded. It is a technique of lowering a string of one or more instruments or logging tools on the end of a wire line into a borehole and recording petrophysical properties using a variety of sensors. The figure here is an example of a wireline tool provided by Halliburton. The logic suite provides us the standard range of logs from caliper, gamma ray, resistivity to porosity, that is neutron and density. LWD and wireline tools and services are also provided by other service providers in the oil and gas industry. Now, for the differences between LWD and wireline logging. The major differences stem due to the differing timing of their use. While LWD is carried out while drilling, wireline logging is carried out after drilling of the section has concluded. As a result of this, wireline logging utilizes additional rig time, while LWD is less time consuming. Another important point to be noted is that the LWD tool or sensors form a part of the bottom hole assembly. Because of this arrangement, LWD possesses some advantages over wireline logging. These are: number one, LWD is very useful for directional or horizontal wells, while wireline is preferred for vertical wells. This is because an LWD tool can provide better depth accuracy and improved well placement during a directional survey. Also, during the drilling phase, the drilling mud is in constant movement in the wellbore, due to which issues such as tool stuck up or mud invasion into the formation can be largely negated. On the other hand, these are major issues encountered in wireline logging which lead to severe NPTs. Now, the fact that LWD tool forms a part of the BHA also negatively impacts the value of an LWD survey in the following manner. The most important is that only basic tools such as directional tools, caliper, gamma ray, and porosity can be attached to the BHA, as adding more tools increases the weight on bit, which in turn will necessitate the use of a higher horsepower rig than required. However, even advanced logging tools such as NMR, FMI, and CPL-VDL can be run using wireline and small horsepower rigs. Also, during the drilling phase, the borehole environment is constantly changing. That is, it is dynamic in nature, and hence the associated vibrations or movements produce more noise than in a nearly static wireline logging borehole environment. Based on all of these advantages and disadvantages, it is observed that LWD is more expensive and constitutes greater risk than wireline logging. LWD is usually preferred only for wildcat and exploratory wells where we do not have much understanding about the subsurface, while wireline logging is carried out for development wells as well. Lastly, both LWD and wireline logs can be carried out under normal as well as HPHT conditions. Coming to the objectives of LWD and wireline logging. These are mainly lithology identifying whether the formation is a sandstone, shale, carbonate, salt, or hard rock. Then determining reservoir properties such as porosity, permeability, and fluid saturation. Differentiating between source and non-source rocks such as sandstone and shale. Identifying the fluid type, whether water or hydrocarbon is present. Delineating pay zones and pay thicknesses, that is, identifying the exact depths at which hydrocarbon occurs. Locating fluid contacts. This involves marking the depth of the last known hydrocarbon or the depth at which fluid changes from hydrocarbon to water in the formation. Lastly, the logs are used for well correlation in order to determine the areal extent of a reservoir. This takes into consideration the formation attitude, facies variation, both vertically and laterally, and the depositional environment. Now, for any particular depth interval, it is imperative to carry out the following essential deductions. We need to first delineate a reservoir from a non-reservoir. A reservoir usually has high porosity, whereas a non-reservoir has low porosity. Once you identify the reservoir, the next deduction is to determine the fluid type and saturation. Water, being usually saline in the formation, is highly conductive and hence low resistivity, and it has high water saturation. Hydrocarbon, on the other hand, is highly resistive and has low water saturation. Lastly, we need to identify whether the hydrocarbon is oil or gas. Oil tends to be more dense than gas. The depth of investigation and vertical resolution. Depth of investigation is defined as the distance away from the borehole that a logging tool can measure. Vertical resolution, on the other hand, is the minimum thickness of a formation that can be distinguished by a tool under operating conditions. This figure is self-explanatory in terms of depth of investigation and vertical resolution. Now, when the size and spacing between the source and the receiver sensors is small, such as in a micro-resistivity log, the result is better resolution, which is 2 to 5 centimeters, but poor depth of investigation, which is less than 20 centimeters away from the wellbore. On the other hand, when the size and spacing between the sensors is large, for example, lateral logs or induction logs, the result is poor vertical resolution, that is, formations or beds that have thicknesses lesser than 80 centimeters will not be identified clearly by lateral logs or induction logs. However, they give us better depth of investigation, which ranges from 1.7 to 2.5 meters into the wellbore. Sonic, density, gamma ray, and neutron logs have resolutions and depth of investigations between the above two. I now come to the next section of my presentation, which will be a discussion on the various basic logs: caliper, spontaneous potential, and gamma ray logs. A caliper log measures the size and shape of a borehole along its depth. It is an important indicator of caving zones and swelling shales. It is an indicator of good permeability and porosity zones due to the development of mud cake in association with the gamma ray log. It is finally also used to calculate the volume of cement needed behind the casing. The figure here is an example of caliper log and associated formation. Under ideal conditions, the caliper log follows the trend of the bit size. Any variation from the bit size will indicate an issue. For example, while drilling through a brittle shale, pieces of the formation break and cave, leading to a higher than bit size caliper reading. Similarly, if salts are drilled using freshwater muds, the salts will be soluble in the water, giving rise to a caliper that is greater than bit size. A lower caliper reading will be obtained under two conditions: a highly permeable sandstone or a limestone, in which case a mud cake is formed along the borehole wall, causing very low caliper reading, or swelling of the clay minerals in a shale when water-based mud is used while drilling. Both of these can lead to reduction in caliper than the bit size. The caliper will read on gauge, that is, the caliper reading will be similar to the bit size reading in well consolidated and non-permeable formations such as massive sandstones or limestones, igneous and metamorphic rocks. The next is spontaneous potential log. It measures the electrical potential in the formation caused by salinity difference between the drilling mud and formation fluid. It is used to delineate permeable zones, that is sandstone, from impermeable ones, that is shale. It is used in the determination of formation water resistivity. Now, in this figure, consider cases A and B, where the salinity of your mud filtrate is less than the salinity of the formation water. In such case, resistivity of mud filtrate will be greater than that of water, resulting in negative SP development. In this scenario, if the formation is a shale, then the SP reading will tend to be low, while if the formation is a sandstone, the SP reading is high. For case C, where the mud filtrate salinity is greater than formation water salinity, we will have resistivity of mud filtrate less than resistivity of water, implying that the SP developed is positive. Now, if the formation is shale, then the SP reading will be high, while in a sandstone, the SP reading will be low. When mud filtrate salinity is the same as formation water salinity, then the resistivities will be the same. As a result, no SP will be developed. In this case, we will not be able to distinguish between a shale and a sandstone. SP logs can also be used to calculate the shale volume or the V shale content in a formation. In order to calculate shale volume, the SP shale and SP sandstone values are obtained from the logs. These are the SP values obtained from pure shale and sandstone zones within the whole drill formation, while the SP log reading is the SP reading at a particular depth of interest. Once these values are determined, volume of shale can be determined at the depth of interest by using the formula given. Coming to the gamma ray log. Gamma ray log measures the natural radioactivity from subsurface formations such as uranium, thorium, and potassium content. Gamma ray logs are of two types: simple, where the radioactivity of all three elements are combined to give a single reading, and spectral gamma ray, where the amount of each element contributing to the radioactivity is individually reported in order to do multimineral analysis. The formations identified on the basis of gamma ray logs. Usually, sandstones, carbonates, and evaporites tend to have low gamma ray values, while shales and other organic rich rocks tend to have high gamma ray values. The figure is self-explanatory here, where you can see that sandstones, carbonates, and salts with little to no radioactive elements show low gamma ray reading, while shales and volcanic ashes with high radioactive elemental content show high gamma ray values. The main uses of a gamma ray log are for well correlation, determination of various litho boundaries, evaluation of the shale content, that is B shale, multimineral analysis when spectral gamma rays are available, and the inference of depositional environments. Calculating the shale volume from a gamma ray log. This is similar to the calculation of V shale from an SP log. We need to identify and note the gamma ray values of clean sandstone and shale zones. We also note the gamma ray value at the depth of interest. Based on these values, we can calculate V shale from gamma ray using the formula given. Now, inferring the grain size and depositional environments from gamma ray logs. Gamma ray log trends can also be used to deduce the grain size variation both vertically and laterally, and also the associated depositional environments. A cylindrical gamma ray pattern is indicative of aggrading environments such as aeolian and evaporite deposits. A funnel-shaped or a coarsening upward gamma ray trend implies a regressing environment typical of river mouths, deltas, and shore faces. A bell-shaped or a finding upward gamma ray trend implies a transgressive environment typical of tidal bars and flats and the transgressive shelf. The hourglass or symmetrical gamma ray trend implies alternating pulses of transgression and regression, as is typical of a shore face delta. Finally, the serrated or a saw-teeth gamma ray trend gives us aggrading environments such as fluvial floodplains and deep marine slopes. Now, moving on to the electrical resistivity logs. Before proceeding to their interpretation, it is necessary to understand the borehole environment. When a formation is being drilled, three particular zones are formed around the borehole. These are the invaded or the flushed zone, the transition zone, and the uninvaded zone. Each of these zones contain different fluids and therefore have different properties. Suppose we are drilling a permeable formation using a mud whose resistivity is Rm. Then the mud cake formed along the along the wall of the well bore will have a resistivity of Rmc, while the mud itself will travel into the formation. Now, within the formation, adjacent to the well bore is the invaded zone containing drilling mud as the primary fluid. Thus, the resistivity of the fluid in this formation will be approximately equal to that of the resistivity of the mud filtrate. Farther away from the well bore is the uninvaded zone containing the actual formation fluids. This corresponds to the true resistivity of the formation, which gives us the resistivity of the formation fluid. Resistivity is usually measured in all the three zones and correspondingly called shallow, medium, and deep resistivity, where shallow resistivity is obtained in the flushed zone, medium is obtained from the transition zone, while deep resistivity is obtained from the uninvaded zone. Coming to the resistivity logs. Resistivity logging techniques measure subsurface electrical resistivity, which is the ability to impede the flow of electrical current. Resistivity of a formation is a function of porosity and pore fluid in the formation. The main uses of a resistivity log are to determine the fluid present in the formation. Saline water is highly conductive and hence has low resistivity, while hydrocarbon has high resistivity. Determining water saturation and porosity, and also indicate the presence or absence of permeable zones by the formation of a mud cake. Some common resistivity tools are based on their depths of investigation, where we have MSFL, that is microspherically focused logs for shallow depths of investigation, and lateral logs, that is LLS and LLD, for medium and deep resistivity measurements. MSFL devices are characterized by short electrode spacing of only a few inches. This limits the tool to shallow depths of investigation of only 4 inches. The main uses of MSFL logs are to determine the flushed zone saturation, to determine residual oil saturation, hydrocarbon movability, and estimate invasion diameter when used with deeper resistivity devices. Lateral logs LLS and LLD. They were initially developed for high salinity drilling muds applied to drill through salt layers. Focusing electrode systems are available with deep and medium depths of investigation. The main uses of LLS and LLD are to determine the true resistivity of the uninvaded zone, to distinguish between water-bearing and hydrocarbon-bearing formations, and they have better vertical resolution of thin beds of up to 2 inches. The figure here shows interpretation of the fluid type from a resistivity log. Hydrocarbon and water can be easily distinguished using LLS-LLD, as hydrocarbon is highly resistive while water is conductive and has low R. Calculation of porosity and saturation from resistivity. Archie in 1942 suggested a relationship between resistivity and porosity of the formation as phi raised to m is equal to ARW by RT, where A is a tortuosity factor, M is a cementation factor, RW is resistivity of the pore water, and RT is the true formation resistivity. Water saturation, SW. An Indonesian equation for SW relates formation resistivity, porosity, shale resistivity, and V shale. It is given by the formula below, where VSH is the V shale that we calculate from an SP or a gamma ray log. RSH is the resistivity obtained for a nearby clean shale. Phi E is the effective porosity of the formation, and N is the saturation exponent. Now, these constants of A, M, and N, that is the tortuosity, cementation, and saturation factors, have predetermined values for typical formations. These are basically 0.81, 1.7, and 2 for sandstones, and 1, 2, and 2 for carbonates. Coming to the last set of logs, that is the density and neutron logs. The density log provides a continuous record of a formation's bulk density along the length of a borehole. Bulk density is a function of the density of the minerals forming a rock, that is the matrix, and the fluid enclosed in the pore spaces. The main uses of a density log are to measure formation density, obviously, to calculate the total porosity of the formation. Combined with sonic travel time, it gives us the acoustic impedance, which is used to calibrate seismic data. It is also a very good lithology indicator. High vertical resolution of a density log helps define formation boundaries very clearly. This figure shows us an example of a bulk density log. Interpretation for the same, coupled with the neutron log, will be explained in further slides. This table gives us a typical matrix density for common rocks and fluids. Density of rocks varies from 1.2 to 4.9, as you can see in the table. Fluids have lesser density ranges from 0.2 to 0.85 for hydrocarbons and 1 to 1.2 for water, be it fresh or brine. Neutron log. A neutron tool is a porosity log that measures the concentration of hydrogen atoms in the formation. In clean reservoirs containing little or no shale, the neutron log response will provide a good measure of the formation porosity if liquid-filled pore spaces contain hydrogen, as is the case when pores are filled with oil or water. The main uses of a neutron log are to measure the total porosity, detection of gas in the reservoir, a lithology indicator, and calculation of shale volume. The figure is a typical neutron log with their scale being from 0.45 to minus 1.5. Density neutron interpretation coupled. Lithology. Density and neutron logs are always displayed on the same track and with their scales reversed. This helps in interpreting lithology and porosity of the formation based on their crossover patterns. It also helps us to identify the presence or absence of hydrocarbons in the reservoir. You can see that a shale will have a high density and high porosity. However, a salt exhibits lowest density and very low porosity. Carbonates, on the other hand, have medium to high density and medium porosity. Sands will have a medium density and porosity. However, their densities will be suppressed in the presence of a hydrocarbon, especially gas, as gas has very low density. Density neutron interpretation, total porosity. Using the density log, total porosity can be calculated in the by the below formula, where phi t is total porosity, rho Ma is the matrix density, rho B is the bulk density value obtained from the log, and rho Fl is the fluid density of the fluid present in the flushed or the invaded zone. We can use a combination of density and neutron logs also to obtain the total porosity. For water and oil zones, phi t is defined as phi d plus phi n divided by 2, where phi d is the porosity derived from density log, whereas phi n is the neutron log reading. For gas zones, the equation differs as phi t is equal to 2 phi d plus phi n by 3. Coming to the final section of my presentation, which is qualitative and quantitative interpretation of the well logs. This slide enumerates the general log responses by different lithologies and fluids. You can see that sandstones, carbonates, and salts have low gamma ray values, while shale and coal have very high gamma ray values. Shale has low resistivity, while salts and hydrocarbons have very high resistivities. Now, coming to the most important part. Interpretation of LWD or wireline logs in a qualitative manner can be easily done based on the direction in which each of the log curves deflect, be it to the left or the right in the following sequence: gamma ray, resistivity, density, and neutron. This method has been devised by the famous petrophysicist Ko Ki, and it has been passed on by a student, Dosh Nazlan, in 2016. The first rule is that for a tight non-reservoir, where the deflections will be right, 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 and right. Gamma ray will deflect to the right because in hard rocks, radioactive content is high and hence gamma ray readings will be high. Because the formation is also tight, the resistivity will be high, whereas the density and neutron porosities will be low. The second is the identification of a shale, where the deflections will be to the right, 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 and left. Gamma ray will show high radioactivity in shale, and resistivity will also be high due to the tight formation. Density porosity will be low because of less pore spaces, but neutron porosity, on the other hand, will read high values because of large clay-bound water present in the formation. The third is a tight reservoir or a low porosity reservoir, where the deflections will be to the left, right, right, and right. Gamma ray will show low radioactivity in sandstones and hence less gamma ray values. Because the formation is tight, the resistivity will be high, whereas the density and the neutron porosities will be low. Now, coming to a water-bearing reservoir, the deflections will all be to the left. Gamma ray will show low gamma ray values in sandstones due to low radioactivity. The resistivity will be low in saline formation water, whereas the density and neutron porosity will be high in a reservoir zone because it is a sandstone which is highly porous and permeable. I finally come to the hydrocarbon bearing zones. For an oil bearing reservoir, the deflections will be left, right, left, and left, where gamma ray will show low radioactivity, resistivity will be high due to non-conductive oil, density and neutron porosities will be high in the reservoir. Lastly, a gas-bearing reservoir will deflect left, right, left, right, where the low radioactivity is observed in sandstones. High non-conductive gas will have high resistivity. Density will be low, mainly because gas has very low density and therefore it suppresses the density of the sandstone itself. Neutron porosity will also be low in a gas. I now come to the quantitative interpretation. The quantitative interpretation of LWD and wireline logs involves a specific workflow which is as follows. Firstly, calculation of the temperature gradient in the formation. This is followed by V-shale, effective porosity, permeability, and fluid saturation calculations. Next is applying various cutoffs for these calculations. And lastly, reservoir summation is carried out. So basically, the first thing that you will do when you are doing log interpretation is to determine whether you have a reservoir or not at your depth of interest. If it is a reservoir, you will then go on to determine whether or not it is a good reservoir. Now, if it is a good reservoir, this will be determined based on the porosity and permeability values that you have obtained from the logs. If it is a good reservoir, then you will go on to determine the type of hydrocarbon or fluid present in the reservoir. Once you determine that a hydrocarbon, that is an oil or a gas, is present in the reservoir, then you will go on to determine the LKH, which is the last known hydrocarbon depth in the reservoir, based on various petrophysical parameters. This then leads to reservoir summation, which is then followed by testing or production, respectively, for a wildcat exploratory or development well. I am sharing an example here with you of a well in Western Offshore Basin, India, where caliper, SP, resistivity, density, and neutron logs have been used to delineate the lower and upper hydrocarbon as well as water zones in the formations, determining the fluid type and the fluid contacts, and carrying out reservoir summation along with verification from core analysis. Various cutoffs used are as follows. The V-shale cutoffs for a clean sand and a silty sand are given below, and the effective porosity cutoff being greater than 10% and saturation less than 5% for a P50, that is a best case reservoir summation scenario. I finally thank you and invite questions regarding the presentation.
Thank you so much, ma'am, for this wonderful presentation. Now we will go ahead and take some questions. So if anyone have any question regarding the topic, you can drop in the chat box. So we have our first question. Why wireline logging measurements are taken from bottom to top?
Okay. You mean to ask this in the sense that wireline logging measure, why are they taken from the bottom to the top and not from the top to the bottom?
Yes, ma'am.
Is that your meaning?
Yes, ma'am. Yes, ma'am.
Okay, so this is basically because you need to lower down the tool and from the bottom up is how the readings are obtained.
All right, ma'am.
Yeah.
Our next question is how to determine the basic shale line as a reference to measure.
How to determine the basic shale line as a reference to measure. The shale baseline is basically the shale value obtained for a clean formation in, during your drilling.
Okay, ma'am.
Yeah.
Could you please explain the mechanism of measuring resistivity?
Sorry.
Could you please explain the mechanism of measuring the resistivity?
Well, I have exactly actually not included the mechanism and the theory behind the logging, each of the logging for that matter, each of the logging tools for that matter, because that would have, increased the scope of the presentation too much and it would have made the presentation a very big presentation. That is why I stuck in this presentation to the basic interpretation part of the logs, which is usually not shared everywhere. On the other hand, if you go to read books like Asquith or Ryder, you will easily understand the mechanisms for each of these logging tools and their measurements and what are the tools used, what are the types of sensors required for what kind of measurements and everything. All of these details you can easily find in very well written books like Asquith and Ryder.
Okay, ma'am.
Yeah.
Can you please explain briefly about basics of image logging and how to interpret it?
Image logging, like I mentioned at the beginning of the presentation itself, is an advanced logging technique which is currently out of scope of this presentation because it in itself is a very vast topic. Image loggings are basically, I'm giving you an example, such as a formation image logger. So what basically happens in this is it captures images of the formation in various stances, that is 4 or 6 or 8 parts, and it gives us the image of the formation, which is used for determining the attitude of the formation, that is the strike or the dip, the various stresses applied or acting on the formation, and the various fractures present in the formation, if any. All of these details can be obtained from an image log.
All right, ma'am. Our next question is why neutron log measures total porosity, not an effective one?
Neutron log measures total porosity and not effective, mainly because neutron logs and density logs for that matter, take into account the total pore spaces in the formation. The effective porosity, the actual difference between total porosity and effective porosity is that total porosity is just the sum of all the pore volume in the rock. On the other hand, effective porosity is the volume of the interconnected pore spaces. So whether or not my pore space is interconnected or not is not determined by a neutron or a density log. They only tell us whether or not pore space is present and how much pore space is present. That is why they give us total porosity instead of effective porosity.
All right, ma'am. Next question is what is the last known hydrocarbon depth?
Last known hydrocarbon depth is basically based on your petrophysical parameters. For example, when you are going to evaluate, when you're going to log interpretation, uh, yeah, let me take this slide for example. When you're going to log interpretation, based on the various cutoffs that you have input into your software of V shale, effective porosity, and saturation, you will determine a particular thickness for a reservoir zone and a particular thickness for your pay zone. Your reservoir zone includes the zone which contains your hydrocarbon as well as the water in the zone below the hydrocarbon. The depth at which your fluid transitions from your hydrocarbon to the water in the formation is known as the last known hydrocarbon depth. So if you look at this image, for example, you can see that in track number 7, you can see a pay flag and a reservoir flag. The pay flag has been indicated in green, while the reservoir flag has been indicated in red. So here, for this particular example, your last known hydrocarbon depth for the upper hydrocarbon pay zone will be around this depth, which is nearly 7,650. Sorry, 7,008, 7,850 feet. Whereas for the lower hydrocarbon zone, you will see a last known hydrocarbon depth of around 8,420 feet. This is the end of your reservoir. Sorry, this is the end of your pay flag, whereas your reservoir extends further and it contains water.
Okay, ma'am.
Yeah.
Next question is, what is the membrane potential generated in the SP log?
Sorry.
Uh, One second.
I'm
What is
unable
the
to hear you.
membrane potential generated in
Your
the?
voice is cracking, Sata. I'm sorry. I'm unable to hear you.
Sorry, ma'am. Ma'am, now it is audible.
No, it is
Hello.
not. Hello. I can only hear you saying hello. I'm sorry.
Uh, Hello, ma'am.
Yeah, I can hear you.
And now
Yes.
it is audible or not?
Yes, you're audible. Yes.
One second, ma'am. Uh, Ma'am, the question is, what is the membrane potential generated in the SP log?
Membrane potential is the self potential that is developed in the SP log on both sides of the SP. Like I explained to you during an SP log reading, whether the SP will be positive or negative, whether the SP will deflect positive or negative is dependent on the membrane potential, where the SP, that is the spontaneous potential, differs between the electrodes. I can go back to the slide and explain it to you. Just a minute. Yeah, so like I have mentioned here, the SP log measures the electrical potential in the formation caused by salinity difference between the drilling mud and the formation fluid. So basically, the membrane potential that you're talking about is basically the salinity difference that is obtained between, the salinity difference that is obtained on both sides of the membrane that we are talking about, which is the drilling fluid and the formation fluid. So this is basically the SP that is developed, and that based on the resistivities of the formation water and the mud filtrate, and depending on their combination, will either be positive or negative.
All right, ma'am. Our next question is, how can we differ in shale and hard shale?
What do you mean by a hard shale? Please explain.
Ma'am, I don't know. Here it is written in question. Hard
If it,
shale and shale.
what does he mean by a hard shale? If he can explain that, then I can answer this question.
Okay, ma'am. We will move to our next
Or
question.
yeah,
Open hole and cased hole resistivity. No, ma'am. What can be done to provide better details when neutron porosity is done in shale rocks?
What can be done to provide better details when neutron porosity is done in shale gas? What do you exactly mean
Yes,
by better
ma'am.
details? Because what you get from a neutron porosity log is the total porosity. So what I do not understand this question. I'm sorry.
Okay, ma'am. How the calibration of logging tools carried out at site?
That is again, like I mentioned, currently out of scope of this presentation. Calibration itself is a big process. If calibration for each and every tool is done separately, they're not done simultaneously, or there is not a standard format of calibration for all the tools together. They need to be done individually, and great care needs to be taken that they have been calibrated properly. So, like I mentioned
O-
before, books like Asquith and Ryder give you all of these details. So you can always refer to them. You will get all the details in these books.
Okay, ma'am. Our next question is caliper log run in open or caged hole?
Open hole.
Okay. Hmm. Can you please explain briefly about basic of image logging and how to interpret
I have
it?
already done this question.
Okay, ma'am. Is NMR logging beneficial in gas hydrate exploration?
Gas hydrate exploration. I'm extremely sorry, but I do not have much info about gas hydrate exploration. I have not worked in gas hydrates before. So sorry,
Okay,
I
ma'am.
cannot answer this.
What does negative neutron porosity indicate?
Negative neutron porosity is basically porosity that we are indicative of very low porosity in the formation. The neutron log basically, like I have mentioned in my previous, not in this slide, sorry. Let me come to the neutron log and I will explain it to you. So like I have mentioned here, the neutron log is based on the calculation of the liquid pore spaces that contain hydrogen. And in this case, when the pores are filled with oil or water, the hydrogen index is 1. So based on this, when you get negative values, it means that your formation is either very tight or it contains very low pore spaces. It could possibly be a massive formation.
Okay, ma'am. Our next question is what is NMR logging and how does it work?
NMR logging, like I said, is the NMR is the short form for nuclear magnetic resonance logging. It is basically a magnetic logging that is used. It is an advanced log, and like I said, all of you are asking me questions about advanced logs which are not part of the scope of this presentation today. Explaining to you the NMR log is going to take a very long time. You can always come back to me. I can provide you my email IDs. At the end of this webinar, you can always come back to me if you have doubts about any of the advanced logs, and we can always discuss about it later.
All right, ma'am. So our last question is how will you differ the tight spot and mud cake in a caliper log as both log interpretations are same as a vertical rectangle thing?
No, both interpretations are not the same as a vertical rectangle. Let me explain it to you here. Yes. Now, you are asking me the difference between a tight spot and a hello,
Yes, ma'am.
hello,
Hello,
hello.
ma'am.
Yeah, hi, hi.
I'm
Can you
audible to
please?
you.
Yes, you are audible. Can you please repeat the question?
1 second, ma'am. How will you differ the tight spot and mud cake in a caliper log as both log interpretation are same as a vertical rectangle thing?
See, basically, when do you obtain tight spots? When your tight spot is basically a situation where probably your tool gets stuck up. Okay. whereas a mudcake formation is separate. A mudcake formation is formed or takes place along the wall of your well bore in a permeable formation like a permeable sandstone or a limestone, whereas a tight spot can also occur when you're drilling through a shale and the shale is swelling because of the use of water-based mud. So in addition to the caliper log, you will also use the gamma ray log in order to determine the lithology, and then you will come to a conclusion whether the tight spot is because of the formation of a mud cake or is it because of the swelling of the shale that you are drilling through. So based on this, you can identify or differentiate between a mud cake formation and a swelling shale or a tight spot.
All right, ma'am. Thank you, ma'am, for this wonderful session.
You're welcome.
And I am on the behalf of Petroleum Engineers Association thanking you all that you all join us for today's session. Now, before leaving, please fill the feedback form which is already shared in the chat window. Thank you, everyone.
Thank you everybody for attending the session today. I hope it has been useful to all of you.